Oh, welcome to 7.4. We're going to do arc length and surfaces of revolution. Now, arc length, we think of measuring a line. We can measure a line. We have a distance formula for lines, but curves, we don't quite have a formula for that. Like an arc like this, we can now use the tools in calculus to determine the length of one of these. So, first of all, a rectifiable curve is a curve that has a finite arc length. So it's not a continuous one. It's finite. It's fixed. Definition of arc length: let the function given by y equals f of x represent a smooth curve on the interval from a to b. The arc length of f between a and b is little s. So little s is integral from a to b of the square root of 1 plus, get this, f prime of x squared. So the f prime of x gets squared under the radical dx. Similarly, for a smooth curve given by x equals g of y, we don't see these as much. We're used to seeing things y equals f of x, but x equals g of y, the arc length of g between c and d is x equals integral from c to d of the square root of 1 plus g prime of y squared dy. So we're going to find the arc length of the graph of the function over the indicated interval. In example 1 here, a little curve. So it's y equals 2/3 times x to the 3/2 plus 1 is how we define this. And x equals 0 to x equals 1. So we have to find y prime first of all. That's going to be 2/3 times 3/2 x to the 1/2. So y prime would just be x to the 1/2. S is going to be the integral from 0 to 1, of the square root of 1 plus x to the 1/2 squared dx. It's 1 plus x dx. Integral from 0 to 1 of 1 plus x essentially to the 1/2 dx. So the antiderivative of that's going to be 1 plus x to the 3/2 divided by 3/2 from 0 to 1. So that s will be equal to 2/3 times the quantity 1 plus x to the 3/2 from 0 to 1, which is 2/3 times 1 plus 1 to the 3/2 minus 1 plus 0 to the 3/2. That's 2/3 of what? This is 8, oh, sorry, 2. 2 cubed is 8, we're doing the square root of that. So square root of 8 minus 1. And that would be approximately 1.219. The exact value for us math people, and the decimal approximation for you physics, chemistry, and even biology and engineering majors. Okay. Okay, so we take the derivative, put it in the formula, proceed through our integration. Find the arc length of the graph of the function over the indicated interval. Y equals natural log of sine of x from pi over 4 to 3 pi over 4. So y prime is going to be what? 1 over sine of x times the derivative of sine is cosine of x. That's cosine of x over sine x, which is cotangent x. So s would be the integral from pi over 4 to 3 pi over 4. It's the square root of 1 plus cotangent of x squared dx. This is, now what is 1 plus cotangent squared of x? That's cosecant squared x. So we just get cosecant x dx. Cosecant x, there we go. So s would become, if you look this up on the chart, that's going to be the negative natural log of cosecant x plus cotangent x from pi over 4 to 3 pi over 4. That's negative natural log of cosecant of 3 pi over 4 plus cotangent of 3 pi over 4 minus the negative natural log of cosecant of pi over 4 minus cotangent of pi over 4. That's going to be the negative natural log of, and I should have had absolute values here to be technically correct. Cosecant of 3 pi over 4 is square root of 2. Cotangent of 3 pi over 4 is negative 1, so we minus 1. Plus the natural log of the absolute value, this is going to be square root of 2 plus 1. This comes out to be 1.7627. So this is the exact answer here versus the decimal approximation. And we could do a little bit more with this algebraically. It would be natural log of the square root of 2 plus 1 over square root of 2 minus 1. Because this negative here, it puts that down below. If you want to combine it under one natural log. Okay. Go on to example 3 here. So here we're going to graph the function, highlighting the part by the given integral. Find a definite integral that represents the arc length of the curve over the indicated interval, and observe that the integral cannot be evaluated with the technique studied so far, and then use our calculators to do it. Okay, so if I graph this is a parabola that opens down. We're looking from x being 0 to 2, so it's first quadrant. There's 2, here's 4. So we want this arc length. Y prime is going to be negative 2x. So part B, here's our part A. Part B is going to be that s equals integral from 0 to 2 of the square root of 1 minus, or 1 plus negative 2x squared dx. That's 4x squared dx. So C, if you put this in the TI-89, I think you could put it on Wolfram. It's a Wolfram thing too. So S would be equal to, and we do our integral, and it gives us a parenthesis. And we do our square root of, and gives us a parenthesis. 1 plus 4x caret 2. This is 4, I guess 4x is fine. Comma x, comma 0, comma 2. So S is approximately 4.647. Let's go on to the next one. Find the total length of the graph of the asteroid. X to the 2/3 plus y to the 2/3 equals 4. So the shape of this looks like the following. So x to the 2/3 plus y to the 2/3 equals 4. Means y to the 2/3 equals 4 minus x to the 2/3. Y equals 4 minus x to the 2/3 to the 3/2. So let's find y prime. That's going to be 3/2 times 4 minus x to the 2/3 to the 1/2 times, and this derivative here will be negative x to the 1/3 times 2/3, because that power that comes down. Oh, sorry, that's a negative 1/3. So y prime is going to be negative quantity 4 minus x to the 2/3 over x to the 1/3, because the 3/2 and the 2/3 cancel. So let's talk about the radical part. Let's talk about that, clean it up a little bit. We're going to have 1 plus quantity negative of 4 minus x to the 2/3 over x to the 1/3. We're going to square that part. That becomes 1 plus oh, I forgot this is to the x to the 2/3, I forgot the 1/2. The negative goes away, the 1/2 and the squared cancel, gives us a 4 minus x to the 2/3, and down below we have x to the 2/3. So what we have here is 1 plus 4 over x to the 2/3 minus x to the 2/3 over x to the 2/3. So this part right here is just 1. So it's 1 plus 4 over x to the 2/3 minus 1. Those subtract out. We have 4 over x to the 2/3. And make sure that this is 2. There. So s will equal the integral from 0 to 8. We're going to multiply this by 4. We'll get one of these and multiply it by 4 to get all of them. The square root of 4 over x to the 2/3 dx, which is the integral from 0 to 8, of 2 over x to the 1/3 dx. That's going to be the integral from 0 to 8 of 2 times x to the negative 1/3 dx. That becomes 2 times x to the 2/3 over 2/3 from 0 to 8. 2 divide out. So you have 3 times the quantity, 8 to the 2/3 minus 0 to the 2/3. It's 3 times the cube root of 8 is 2. 2 cubed is 4. So you get 12. We have 4 of these. So 4 times 12 equals 48. Whew, that was a rough one there. So we had to solve for y. We had to take the derivative, put it under the radical. This is the stuff that would be under the radical. Simplify that. I thought it'd be nicer to do that separately and then come up with our final result that we plug in here. Then we integrate, and that wasn't so bad to integrate. Dealing with this was not so pretty. So we've talked about the arc length on several different examples now. Now we want to talk about a surface of revolution. In previous sections we talked about volume. This is talking about a surface. Imagine a line being rotated, not an area now. A line's rotated. You're going to have a surface of revolution. So if a graph of a continuous function is revolved about a line, the resulting surface is a surface of revolution. So you spin it around, it'd be like a hollow bowl or something. Definition of the area of a surface of revolution. Let y equals f of x have a continuous derivative on the interval from a to b. Let the area S of the surface of revolution formed by revolving the graph of f about a horizontal or vertical axis is S equals 2 pi times the interval from a to b of r of x times the square root of 1 plus f prime of x squared dx. So this part's what we've seen before. Now we have r of x, which is our radius. So it's the distance between the graph of f and the axis of revolution. And so y is the function. Now, function of x, in this case x is a function of y, x equals g of y. It's 2 pi integral from c to d r of y times the square root of 1 plus g prime of y squared dy. Again, r of y is the distance between the graph of g and the axis of revolution. So let's do a couple of examples here. Set up and evaluate the definite integral for the area of the surface generated by revolving the curve about the x-axis. So this looks something like the following. And it doesn't say it's supposed to be from 0 to 3. I forgot to type that in here. So it's going up to 9. It's going about the x-axis. So our y prime is going to be 1/3 times 3x squared, or just x squared. Now r of x, that's just going to be our 1/3 x cubed. So the surface area is 2 pi times the integral from 0 to 3, 0 to 3 for the x, of our r of x, which is 1/3 x cubed, times the square root of 1 plus x squared squared. This is our y prime squared dx. So it's going to be, I'm going to pull this 1/3 out. 2 pi over 3 times the integral from 0 to 3 of x cubed times the square root of 1 plus x to the 4th dx. So this is interesting because if I'm doing a u substitution, u is 1 plus x to the 4th, du is 4x cubed dx. So integrating this is kind of nice. We can treat this, let me go one step further. S is 2 pi over 3, integral from 0 to 3 of, I'm going to put a 1/4 out front and do a 4x cubed. In fact, let me go this other way. Square root of 1 plus x to the 4th times 4x cubed dx. So the 4 cancels the 1/4. This gives me pi over 6. It's 2 pi over 12 is pi over 6 times 1 plus x to the 4th to the 3/2 times the reciprocal 3/2, which is 2/3, from 0 to 3. So S would be equal to pi over 9 times 1 plus 3 to the 4th, that quantity to the 3/2, minus 1 plus 0 to the 4th, to the 3/2. Okay, so 3 to the 4th is 81 plus 1 is 82. So we end up with pi over 9 times 82 to the 3/2 minus 1. And that would be approximately 258.85. There are the two answers. Okay, we got one more to do. Set up and evaluate the definite integral for the area of the surface generated by revolving the curve about the y-axis this time, not the x-axis. Nine minus x squared is another parabola. And the interval here wasn't stated. I'm going to say 0 to 3 for x. This is 3, this is 9. Okay, so this curve is defined by y equals 9 minus x. This distance here, this r of x, would just be x. How far we are from the axis. It's going to be a distance of x. So we could have resolved this and make it say x equals something in terms of y, but I think it's going to make it more complicated. Therefore, what do we want to do next? S equals 2 pi times the integral from 0 to 3, if we keep it in terms of x, of our r of x, which is x, times, well, what's y prime? Isn't that negative 2x? So it's x times the square root of 1 plus negative 2x squared dx. So it's x times the square root of 1 plus 4x squared dx. And if it helps to see it this way, the derivative of 4x squared is 8x. We have x dx, not 8x, so we could say s equals 2 pi times the integral from 0 to 3 of the square root of 1 plus 4x squared times 8x dx. But I can't just put an 8 there, I have to put a 1/8 out front. 1/8 of the 8, they cancel. So we end up with pi over 4 times what? This is the derivative of the stuff inside. So it becomes 1 plus 4x squared to the 3/2 times 2/3 from 0 to 3. Okay, so 2/3 times pi over 4, I believe is pi over 6, times 1 plus 4 times 3 squared to the 3/2 minus 1 plus 4 times 0 squared to the 3/2. Okay, let's see, 3 squared is 9 times 4 is 36 plus 1 is 37. So it's pi over 6 times the quantity 37 to the 3/2 minus 1. And our decimal approximation is 117.319. Okay. And that's the end of 7.4. I hope you liked it. I kind of like it. It's a little change of pace from what we did with all the volumes. So send me your questions. I'll talk to you guys later. Bye.